So we should be right below example 2 is where we're going to start in today. So 9.1 part 2. Now I'm just going to remind us, quadratic function is something that we can write y equals ax squared plus bx plus c. When we have a function that looks like that, that's a quadratic function. Now, in terms of the graph of the quadratic function, the coefficient on x squared, this number, coefficient means number in front of, the coefficient on x squared determines the width of the parabola. So the bigger the number that's in front of the x squared, the narrower the parabola. And the smaller the number, the wider the parabola. So a fraction, this says a fraction for a, makes the parabola wider. So you might see a problem that says in order from narrowest, widest to narrowest, we want to put these in order. So the smallest number makes this narrower. Well, this, the 4, that's the biggest number. So that's going to be, the one with the 4 here is going to be the widest. And here we have a 2. That's smaller than 4. But these are fractions, so these are going to be even smaller. So this is going to be the second widest. Yes?
Does the negative or positive matter?
It doesn't matter. Remember the negative in front of the number in front of the a squared determines whether it opens up or down. So the negative would just turn it upside down, but the number itself is what decides whether it's wide or narrow. Well, now we have to decide between 1/3 and 1/8 which one is bigger and which one's smaller. Do we know? Is 1/3 or 1/8 smaller? 1/8 is smaller. If you divide by a bigger number, you get a smaller number. If you're not sure, you could put this in your calculator and say 1 divided by 8 is 0.125, and 1 divided by 3 is 0.33. So this is the smallest. So this is going to be the I did this backwards. This is the biggest number. This is going to be the narrowest. This is going to be the second narrowest. So this is going to be the widest. And this is going to be second widest. So if we put these in order from wide to narrow, this would be number 1. That's the widest. This would be number 2. That's the second widest. Then we get number 3, and that would be number 4. From widest to narrowest. So a fraction makes our parabola wider. A bigger number makes it more narrow. So now we know the negative in front of the x squared part makes it open up or open down. The number decides whether it's wide or narrow. Now we're going to talk about how we move our graph up and down on the y-axis. So that's what the next part of the note sheet is about. Let me make this a little smaller. 100, there we go. So if we have graphs, I'm going to kind of go out of order here. If we have graphs or functions that look like y equals ax squared and y equals ax squared plus c. So these are quadratic functions with no b part. I would say no bx part. We have no bx part for our quadratic. The y-axis is the axis of symmetry. So our graph is going to be symmetrical about the y-axis. The c part moves the graph, translates or moves the graph up or down. A positive c moves it up, and a negative c moves it down. And we saw something similar to this when we graphed absolute value functions. We talked about how they shifted up and down and left and right. And when we had something added outside the absolute value, if it was positive, it shifted the absolute value up. And if it was negative, it shifted the absolute value down, the V-shaped graph. Parabolas are exactly the same. This C out here at the end, if it's positive, it moves our graph up. If it's negative, it moves our graph down. So you might see questions that say, how would these graphs be different? How would graph B be different from A? Well, we have a +3 here. This first part is the same, so we would say this is moved up 3. That's how this graph would be different from this graph, because everything else is the same. And we'll draw little sketches here of this in just a second. Well, here we want to know how A and B are different. Well, the 1/3 x squared is the same, but this has a -5. So this would be shifted down 5. And if we drew a little graph, I'm just going to sketch a basic graph here by hand. If I plug in 0 here, when x is 0, y is 0, so we get a point here. And when we plug in x is 1, 1 squared is 1, times 2 is 2. Oops, so I go up here. And this is symmetrical about the y-axis. The y-axis is the axis of symmetry. So I can reflect that point over. And that graph would look like this. That would be y equals 2x squared. If I wanted to graph this graph, it's going to go up 3 units. So my vertex would be here. And I would get a point. My new point, this point would be shifted up 3 also. 1, 2, 3. Here, I'll do this in red. This point would be shifted up 1, 2, 3, like so. And my new graph would look like that. Y equals 2x squared plus 3. Everything just moves up 3. For this one, If I plug in 0 for x, well, 0 squared is 0 times 1/3. I get a 0. My vertex is there. And I'm going to plug in x equals 3. So I get a nice number that I can divide by 3. Well, 3 squared is 9, and 9 divided by 3 is 3. So I get a point at 3, 3. And then we get a point over here at negative 3, 3. And to graph this graph, I'm just going to shift all these points down 5 units. So I get a point here. This is shift down 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And there would be y equals 1/3 x squared. And there would be y equals 1/3 x squared minus 5. Everything is just shifted down 3 units. And we can see that this one with the 1/3 is wider than this one with the 2 in front of the x squared. All right, we good there with our shifting our graph up and down. All right, so let's look at the example below this one. We have a problem about someone dropping a rock into a lake, and they give us a function that describes the motion. Oops. And I mentioned on Friday that quadratic functions describe how objects move close to the surface of the Earth. So we drop a pebble at a height 30 feet above a lake, and it says the function h equals negative 16 t squared plus 30 gives the height of the pebble after t seconds. We want to know about what time the pebble will hit the water, and we're going to sketch a graph of this function to figure out when the pebble hits the water. So if we're dropping something into a lake from 30 feet up, so we're 30 feet above the lake. When it hits the water, what is its height? 0. We want to know when is the height 0. When is the height equal to 0? If we're 30 feet above, when it hits the lake, the height is 0. So if we're talking about an equation, we'd be saying, well, when is negative 16 t squared plus 30 equal to 0? That's another way we could ask this question. And we'll talk about in a couple of sections, we'll talk about how do we solve that equation. Today we're just going to solve it by graphing. So I'm going to make a graph here. I'm going to make a table of values. So I'm going to say t and h equals negative 16 t squared plus 30. That's where we're going to calculate our h values, and we'll put our h over here. And we're going to start at time equals 0. We're going to say that when we let go of the pebble, time equals 0. So at time equals 0, what should our height be at time equals 0? When we're starting?
30.
It should be 30. Well, let's plug in 30 here. Negative 16 times 0 squared plus 30. Well, 0 squared is 0 times 16. We get 30. That's good, just like we expect. Now we'll plug in a couple of times. T equals 1. So we get negative 16 times 1 squared plus 30. And 1 squared is 1, so 16 minus 30 is 14. plug in 2, negative 16 times 1, sorry, 2 squared, plus 30. Well, 2 squared is 4, times 16 is negative 64, plus 30, and I get negative 34. So sometime between time equals 1 and 2 seconds, my pebble is going to hit the water. So let's sketch a graph. We might be able to get a little better idea if we sketch a graph. I'll go by 5, 10, 15, 20, 25, 30. And I'll go by seconds, 1, 2, 3. So I get a point at 0, 30. I get a point at 1, 14. So that's going to be right about here. And if I connect those with a nice smooth curve, I get something like that. And I would guess here maybe a little less than 1.5 seconds. It's not quite halfway in between those. Maybe 1.3, 1.4. So that would be a way that we can estimate when this pebble hits the water. Now what if this problem asks us what the domain of this function is? What t values are we plugging in here? Are we plugging in time less than 0? No. So we're going to say our domain is t greater than or equal to 0. So we plugged in 0. That's right when we start. What about our range? Our y values? Well, where do we start when we have the pebble in our hand? 30. And where do we end? 0. So our range is y between, or I guess I could say h, between 0 and 30. That would be our range, from 0 to 30. I guess we could talk about as the pebble sunk into the water, but the problem doesn't really say anything about what happens after it hits the water. Yes?
What is the difference?
T greater than or equal to 0. All right, the last thing we're going to do is just sketch another graph. Just talk about how we construct a table of values and sketch a graph. Yes? Mm-hmm. This is exactly like what we did on Friday, just our function is a little bit different. Yes?
Is this what we're working on? I don't know.
Yes. So we want to sketch a graph of the function y equals 1/3 x squared plus 2. So we know because of this 1/3, it's going to be kind of wide-ish. We know with the plus 2, it's going to be shifted up on the y-axis. So we're going to plug in some values. For this one, I'm going to say -6, -3, 0, 3, and 6. On the worksheet, that's our homework, the x values for your graphs are already in your table so that you don't have to figure those out. And what we did was we got numbers that work nicely with the function. If it doesn't tell you, if the problem doesn't tell you what x values to use for your table, you should use -2, -1, 0, 1, and 2. Just always. But for the graphs on our homework, we put in what your x values should be so you don't have to figure it out. All right, so I'm going to plug in -6 here. 1/3 of -6 squared plus 2. I'm going to write some calculations down here. -6 squared is 36, so we get 1/3 of 36 plus 2. Well, 36 divided by 3 is 12, plus 2 is 14. Plug in -3. 1/3 of -3 squared plus 2. 1/3 of 9 plus 2. 9 divided by 3 is 3, plus 2 is 5. Plug in 0. You get 1/3 of 0 squared plus 2. Well, 0 squared is 0 times 1/3 is 0. I just get a 2 there. Here I'm going to plug in 3. Can we guess what we're going to get there? We're going to get 5 because our graph is symmetrical about the y-axis. And here we get 1/3 of 6 squared plus 2, which is going to give us 14. So plot these points. I get a point at 0, 2. I get a point at 3, 5. There's 1, 2, 3, 5. And I get a point at -3, 5. There. And this is a point at 6, 14. About here. I'm guesstimating, I'm just extending this up. And I should get a point about here. And there would be a graph of that parabola. I guess I could do these by 2, maybe. 2, 4, 6, 8, 10, 12, 14. I could do it that way as well. I just kept counting by ones. And that would be a relatively accurate graph of this function. So we're stretched out. So we're kind of wide. We're up 2. Let's look at the domain and the range. Now, could I keep going on the positive x-axis and the negative x-axis and plugging in x values to come up with my graph? Yeah. So our domain for this function, because it's just y equals this, is all real numbers. The domain for the last one was t greater than 0 because we're talking about a situation where we're starting at a specific time and we're ending at a specific time. But this one, we're just talking about a graph of this function. The range. Where does my graph start on the y-axis? 2. And it keeps getting bigger, right? This goes up and up and up. It could keep going as far as we wanted. So we'd say the range is y greater than or equal to 2. Because we start here and we keep going up. All right. Questions on graphing quadratics, our basic quadratics? Okay, what we'll talk about tomorrow is what happens when we end up with a bx in our function. How does that affect the graph? Anyone want to guess how that might affect our graph? So we've talked about stretching it, making it wider or narrower, and we talked about shifting it up or down. What other thing could we do to our graph?
Rotate it.
Could rotate it. And what do you mean by rotate? Oh, that's even more complicated. So you probably won't talk about that until you get to pre-calc. That's more, even more complicated. What's a simpler, one simpler that we could do? Yes. Yes, the b value is going to shift our graph side to side. And we'll talk about that tomorrow. We won't talk about rotations, but it gets interesting when you talk about rotations, I think. All right, our homework is a worksheet. 9.1 worksheet. And all the graphs and all the tables are on there for you.